Okay, so first thing, I would like to thank you for joining us today and during these 2 days. Thanks, Stefan, for this introduction. And so it's always nice to have this conference because we can always see the faces of friends, new one or old ones. Not for you, Mike, you are still young, you know that. And also new faces. So welcome, everybody. And as Stefan said, since 2017, I'm just using this conference as a way to introduce the new features we are releasing. So this year, this is BayesiaLab 9. So I just want to focus here on, or during 30 minutes or 45, I don't really know, on BayesiaLab 9, right? So what are the new features you're going to have in a few weeks? So as you can see, 6 main topics: optimization, evidence analysis, prior knowledge, resampling, export, and media. Right? So let's start with optimization. I know if you are familiar with BayesiaLab, you know that we have optimization tools, and there are 2 types of optimization. So either you're optimizing your target node, or our function nodes that we introduced. You want me to talk loud? It's going to be hard because I'm speaking since 3 days nonstop. So either target or function nodes, right? So function nodes are these little green nodes that you have here that works like kind of APIs within Bayesian networks. So I'm going to start with the target optimization. So optimization is in the sense of what is a sequence of action or evidence you can set in your Bayesian network in order to increase the priority of states or increase the mean value of your target or things like that. And we have 3 types of optimization. So the first one is a greedy search, greedy optimization. Then we have also a tree that allows us to explore more decisions. And the last one is a genetic optimization. So for the greedy, here I'm just displaying, it's quite old, this one. This is what we called before the target dynamic profile. I think we had this feature in 2008 or so. But it's still evolving. Every day we are adding features in BayesiaLab, so this one is also evolving. So if you are not 100% familiar with this one, there is this box that allows you to define what you want to optimize. So you can either optimize the state of your target, or you can optimize the mean, or the difference between 2 states. You can also define what are the evidence you are going to use for the optimization. So it can be hard evidence, when you don't have any uncertainty on the states, or it can be mean, so by using numerical evidence. And with that, when you use a very simple one, you want to optimize the priority here. This is a priority of 1 state greater than 4, and I'm using hard evidence for that. So when you do that, so with this one, this is a purchase intent I want to optimize. And I have a sequence of evidence that allows me to increase the priority of this state. So you see, we start with a priority of 28%. So this is what you have here. And then we know that this is personalities that we should observe in order to increase the priority of this state to 51%. So setting a hard evidence on this one allows you to increase the priority of the state 4 to 51%. And with that, you also have the priority of this evidence, which is here 26%, right? And we have also now the priority of this evidence given the states you are optimizing. So if we set evidence on purchase intent greater than 4, you have also priority of this personality greater than 8 equal to 48%. And by using these 2 pieces of information, we are now displaying the base factor. Right? So this is just the ratio between these 2 probabilities. And you have also the generalized base factor, which is the ratio between the base factor of this evidence and this state, and also the base factor of the negation of this evidence and this state. Right? So this generalized base factor is kind of useful. We're going to talk about this one in a few minutes too. And when you use the binary log of this metric, you have what we call the weight of evidence. Right? So this is what you have now here in this column. We have also added some, I don't know if it's, I think it was last year, we added this option. I can also use, instead of using hard evidence, I can use mean evidence, numerical ones. But sometimes, you have all your drivers or all your dimension that can be indeed, where you can indeed use numerical evidence for them, but for some of these, numerical evidence does not make sense, right? So if it's a variable without any ordering, it does not make sense to use a numerical evidence. So now you can define these nodes by using this class, this predefined class, the opt-hard evidence, where you're going to say that for these ones, you are going to use hard evidence instead of numerical evidence. So this way you can mix numerical evidence and hard evidence. So I use this example, even though it's not the best one, but here you have numerical evidence on flurry and spice, but a hard evidence on intensity, right? So you can really mix both now. And the third one is when you are optimizing the mean value of your target node, right? So now it's not just the probability of one given state, but I want to optimize this value, this 3.76, which is my marginal value for purchase intent. So you have this value at the very beginning. And here, same thing, if we set personality to a state that is greater than 8, we are going to increase the purchase intent to 4.5, right? So now you have also the joint here. So this is the probability, the prior here for this state. And we are computing the confidence interval. So before you had the value of the delta, if you want, but now we are displaying the interval, which is much more useful indeed, right? And so this is here with 95% of confidence, but you can use the preferences in order to change it if you prefer to use 99% or 99.9. So you have a long list of choices here that will update this formula. Okay. So this was a greedy search, right? So in order to increase or to have something that is more robust, we have also a tree, a target optimization tree. So this is something that is not, you cannot do that for all the states, so you have to choose either one state or the target mean. And then you have the same thing here, you can define what are the evidence you're going to use for that. And you have a search stop criteria to define here. So this is, the first one is the depth of the tree, how many evidence you're going to use, right? And also what we call the number of skipped evidence, which is, at the end of the day, the kind of the width of the tree, right? So this is working this way. You have your target node here with the original mean value. And on the left, you have indeed the result that is given by the target dynamic profile. So this left side, correspond to the greedy search. And when we are in this one, this is, to generate this one, this is what if, instead of using tenacious, we cannot use it, so the second best choice is original. And if it's not original, then it's woody, right? And same thing at this level. The second best driver was classical, but if we are not going to use it, then the second best one is tenacious. So with that, we are creating lots of profiles. So it's like creating lots of catches at the end of the day, right? And then you can create a report that will summarize the quality of each driver. So this is really like taking the score of these leaves and associating this score with the drivers. So you have not just one optimization policy, but a set of policies, if you want. And obviously, you can also do the same thing with a mix between hard and mean evidence, right, or numerical evidence. So this one, for example, is with intensity is a hard evidence, right? Then the last one is a much more powerful approach because it's a genetic algorithm, right? So in this one, the first thing you can do is you can optimize the states. So because with the target and the targeting profile and target optimization tree, you are just trying to increase either the probability or the mean value. But with the genetic algorithm, you can also define one specific value. So in that example, I want the mean value of my target to be equal to 4. So I just don't want just to optimize it. I want to reach one objective. This is a new feature we added in this version. This is to allow BayesiaLab to not to set evidence for all the nodes, because this was a problem with genetic algorithm is the chromosome was using all the drivers. So sometimes it's not really convenient. So with this option, you can reduce or allow the genetic algorithm just to use a subset of drivers. Right? And we have introduced a filter We are going to talk about this one later too. So this is a filter that will allow you to reduce the list of the solutions that have been generated. So in this example, I'm going to just return the test best solutions, but by using this filter, so either 0, 1, or 2. So 0, obviously, you are not filtering, and then there are 2 levels of filters. So this is the result of the optimization of my mean value here, where I want to have 4, and as you can see, the first solution, I have 4. And you see I'm just using 3 pieces of evidence. The second best solution is only using 2, and so on and so forth. Right? And when you use a filter equal to 1, this is what we call we are removing the strongly dominated solution. So what we mean with strongly dominated solution is a solution that is like this one. You know, this one has more pieces of evidence, and the score is lower. So we are, in that case, assuming that this is strongly dominated because we have more evidence with a score that is not that good. Right? The second filter is filtering the strongly, but also the weakly dominated solutions. Right? So this is when, so a weakly dominated solution is a solution that is more concise, but with a score that is slightly worse. Right? So, but sometimes you are looking for something that is more concise. So this is the reason why you can decide to keep these weakly dominated solutions. So we have here 1 weakly and 1 strongly dominated. And then you have the same thing for the function, right? So you can use a greedy search for optimizing your function nodes. So if you are not familiar with function node, you can really define this as, you know, it can be the mean, it can be the entropy, it can be the joint, it can be anything, but it's a result of inference on your Bayesian network. So it's much more powerful than just using a target node. So we have also the tree for optimizing the function and also the genetic algorithm. So this was for optimization. Now I'm going to switch to evidence analysis, and I'm going to talk about 4 different topics. The first one, also very old one, this is a target analysis report. So I guess you are used to this one. As soon as you have a target, you have this report. So, and I'm going to use this example where suppose that I have a data set of people. So this is the data set we are using during the intro course. So we have a data set that describes people from the US Army. They are doing 7 workouts a day, and we have measurement about their body. And let's suppose you want to analyze this data set to create a latent variable that will allow you to identify groups of people. Right? So here I used data clustering for that, and I found 5 clusters. Right? All these nodes, you know, this is a radial layout that I use within the analysis of the arc force. So this is organized clockwise. So this is the strongest node, well, the one with the strongest mutual information. Then this is forearms and shoulders. So, and this is the weakest one is age. Right? And then when you do data clustering, you are creating a hidden variable, right? So this is a variable that you have. You are adding a column in your data set with 100% of missing values. So the idea, once you have that, at the end of the day, it's to understand what are C1, C2, C3, C4. So you have to interact with your model to carry out inference in order to be able to associate images with these guys. Right? So, and this can be not that easy to reinterpret these factors, right? So I'm going to use this example to show you how you can do that. So the first thing, obviously, is to use the sort, the monitor with respect to the mutual information. So this is the sorted list of monitors with respect to the mutual information based on the entire node here. So we found again that the strongest one is weight and the weakest one is age. And you can also do sort with respect to the target state correlation. So this one is sorted with respect to C1. So it's really like creating a dummy variable, C1 versus all the other one. And now you can see that the order is different because it depends only on C1. So these are the variables that are really useful for discriminating between C1 and all the other one. Right? So now, see, gender is the most important driver. And then when you have this target, you can generate this target analysis report. And this is right now focusing on C1. So I have, again, this gender at the very top of my list because it's using the binary mutual information. So this is really again, by using the dummy variable C1 versus the other one. And we have now also two columns, so the max Bayes factor and the mean Bayes factor. So here, a reminder of the formula. So the Bayes factor, ratio between the probability of the evidence given C1 and divided by the probability of the marginal probability of this evidence. So this is here, the Bayes factor for gender is equal to 100% divided by this marginal 148%. So this is 2.053, right? And the negative one is the one that the states that decrease the most, right? So we are also computing the Bayes factor for this one. And as you can see, this is color coded. So red, this is the first state, green, the last one, and in between you have this palette of colors, right? Now I'm gonna just, it's not new here, the MP, but it's more like a way to describe the journey to the new feature I'm going to introduce in a few minutes. So the most probable explanation, so this is also called the maximum a posteriori, it returns the fully instantiated evidence that has the highest probability. So those who went to my training are familiar with this representation of the joint probability distribution. So remember that a Bayesian network is representing this joint, so we are trying to find the most compact representation of this joint probability distribution. So here it's just an illustration with 3 dimensions, and then I have one variable with 3 states, and the other one 2 states, so I have a hypercube or a cube here made of 12 cells, right? And in this hypercube, the MP will identify the cell with the highest probability, right? So the MP will return this set of evidence. So this MP can be marginal or conditional, so which means that you can set evidence and you are going to have the new MP given this evidence. So this is an example here with these 3 nodes. And when you switch to the MPE mode, the monitors are not displaying any more probabilities, right? So these are more factors. So 100% mean this state belongs to the MP. So with this network, the MP is having a senior non-smoker without bronchitis. And here this is, given it's a small joint, I was able to compute all the probability of all the events. And this is a sorted list of these events. And you can see that indeed, the cell with the highest probability is senior, non-smoker, no bronchitis. And the second one is adult, non-smoker, no bronchitis, with a joint of 14%. So there is a factor of 79% of reduction. So this is what you have here, right? And then 64% that you can see here, this is this one, right? So when you have an adult, a smoker, and bronchitis, right? So now, if I set a hard evidence on young adult, I'm going to switch to this slide, right? And I'm going to reduce the joint, or the joint probability of the new evidence that has the highest probability to 10%, 10.7%. So I'm reducing it by 59%, right? And now the most likely states are smoker and bronchitis, right? So this is how the MP is working. So if I use the MP on my cluster, right, you're going to see that this is kind of counterintuitive, because when you look at this one, you see that the cluster that has the highest marginal is C1 with 25%. But with the MP, this is indeed C5. Right? And this is usually what happens when you have lots of evidence, because we are really looking for the cell in this huge hypercube that has the highest probability. So sometimes it's very hard to understand, right? So the new feature we added in this BayesiaLab 9 is a possibility to instantiate your MP. So you can make just a right click on either all the monitors or just the one you are looking for, and then we are going to set directly instantiate the state with a factor equal to 100%. So those that belong to the MP, right? Then the second thing after the MP, there is what we call the maximum a posteriori, or also called the marginal maximum a posteriori. So this one returns the most likely set of particles, but just on a subset of variables, right? So instead of instantiating all the other one. But this is now very hard to optimize. The MP is very easy to compute, right? So it's just a max across some function. But for the map, it's very hard to optimize. And we don't have any feature for that directly. But given that we have function nodes, it's easy to implement, right? So I'm still here using my example with my cluster, and I want to have the maximum a posteriori for C4, taking into account only 3 dimensions: gender, BMI, and age. So I cannot use the MP for that because it's going to instantiate everything, right? So I just want to focus on these 3 nodes, and for that I've created these function nodes, right? So I have the maximum a posteriori, I have the joint, the number of observation, and the minimum number of observation I want to have in this maximum a posteriori. And the function I use here, so I'm just going to focus on these 2. So, so in function node, you have to go to equation to define what is your function, and to select here inference function. So you have a long list of functions that are available, and for this one, we added a new one that allows you to know how many observations has been set in your network, right? So you can count how many hard evidence, how many numerical evidence, soft evidence, and likelihoods, right? And so here I've defined that I just want to count how many hard evidence I have set in my network. And for the function node MAP, I'm just using this function. So if the number of observation is less than the mean I have defined, then it's going to be 0, and otherwise it's going to be the joint probability distribution. Right? So this way I can optimize the joint just by using the 3 evidence. And I have then this report. So this gives me that the best 3 set of evidence for increasing or for optimizing the joint probability distribution given C4 is BMI less than 22, age less than 24, and woman, right? And I have a joint of 5% if you want here. And then you have the list of the alternative solutions, if you want, that are slightly worse, if you want. Okay? So this is how you can use BayesiaLab for implementing the maximum a posteriori by using function nodes. But you can also use the map without specifically defining what are the nodes you want to use. So I can also say, I want to have the map with only 3 evidence, and I don't care what are these evidence, right? So in that case, I'm not going to select any nodes, and BayesiaLab will search what are the 3 pieces of evidence that allows you to increase the joint given evidence or not. So this one is without any evidence. It's a marginal one. So the 3 pieces of evidence that allows to increase the joint are these 3, shoulder, forearm, and gender. And if I set the evidence on C4, I have a new set of evidence, right? So these are the 3 that allows me to increase the probability given C4. Okay. So you have lots of flexibility once you know how to define your function nodes, right? So function node plus genetic algorithm, you can really do what you want. So this was the maximum a posteriori. And this leads me to the new feature that we call the most relevant explanation, so MRE. And this is not something we have created. So the weight of evidence, this is not something that is quite old, 85, right? So the work from Good. And the article we used for that was the one from Yuan, Lim, and Lu. And so you can, it was published in JAIR in 2011. And so here the idea is to return the most concise explanation for one current set of evidence. So you cannot use it without evidence. Obviously, as the name indicates, you are looking for an explanation. So explanation of something you have defined via the monitors, right? And it's based on the maximization of the weight of evidence I briefly mentioned before. So this is a binary log of the generalized Bayes factor. And this is another way to represent the generalized Bayes factor. This is indeed a ratio between the posterior odds and the prior odds, right? So we are just looking for the maximization of this term. So if we use the MRE with a causal Bayesian network, so which means, you know, my vocabulary here, it's when I'm designing a Bayesian network by using expert knowledge, I'm talking about a Bayesian belief network. When it's a causal Bayesian network, it's a causal Bayesian belief network. When I machine learn a Bayesian network, it's a Bayesian network. And if I tag this network as causal, it's going to be a causal Bayesian network, right? So these four little terms. So this, let's suppose I have a causal Bayesian one. And so this is the example coming from the article I was just mentioning. So we have this system. So this is a network that represents this system. And so this is, we want to know if the output is true, what is the most likely configuration, or what is the most relevant explanation of this output being true. Right? So just keep in mind this scheme here. So we set this output to be true. Then we have this wizard here where you have to define the search space. So you can, if this is really a causal Bayesian network, you are just going to search among the ancestors. But if it's not, you can also search about among the observable Markov blanket or all the nodes if you want. We have here again our filtering power here from 0 to 2. So 0, no filter, 1, strongly dominated, 2, weakly dominated and strongly. And I'm going to return the 10 best solutions, even though we don't have 10. And this is the result we are going to have here. So the most relevant explanation for the output being true is going to be the B and C being defective. Right? And then the second one is A being defective. And then this is B and D, and then just B or C or D. Right? So this looks like something obvious, but it is not at all. Right? So it's really not easy to compute, or at least to search, because this is a very huge space here. And these three last scenarios will be indeed deleted if you use a filter equal to 2, because they are weakly dominated. You can see that the set of evidence is smaller than the best solution, and the score is slightly lower. Right? So, but if you are really interested in something more concise, you can also consider these three solutions. Okay. So this is an example with a causal Bayesian network. And here I can also use it for trying to analyze my cluster, right? So here, let's suppose I want to analyze C4. So as you can see here, I have in my monitors, I'm not sure you are aware of these features. This is something we added 2 or 3 years ago. So you see these are not probabilities, but rather delta. So setting C4 increases the probability for weight to this state 66, right, and decreases the first one. So you have all the delta, so it can be a very convenient way to analyze the impact of setting evidence in your monitors, right? And if you use the MRE for that, you're going to have this set of solutions. So it's concise, so it's the best one is weight, so this was the second state that was there. The second one is woman, and then you have all the different combinations with a score, right? So very convenient for analyzing clusters. And we're going to have a third example, but I'm going to let my friend Michael do that tomorrow afternoon at 4, because he's going to present something called Understanding Your Customers Through the Most Relevant Explanation Function in BayesiaLab. So I guess this would be something very, very interesting. So this was for evidence analysis. Now let's switch to prior knowledge, which is something very interesting. And I'm sorry for those who are bothered with my particles, but here they are again. So you know, for me, a joint is populated by particles. So a particle is one instance of your domain. Right? So it can be a patient, it can be a customer, what have you. So this is one instance of your domain. And these particles, either you have access to this particle via expert knowledge, right, or via structured data sets. So when it's via structured data set, it's easy because you already have all the dimensions that define the perception of this dimension, of this particle, sorry. But when it's coming from expert knowledge, you have to brainstorm and to find what are the dimensions that are going to be useful for describing your particles. Right? But let's suppose we have the perception. Now I'm going to talk about 3 ways to handle prior knowledge. So the first one is directly. So directly prior, You know, this is like adding virtual particles, right? So this is obviously more when you valid when you have data. So in that way, we are still using the maximum likelihood, but we are integrating pseudo counts that comes from these virtual particles. So this is like in my estimation of theta here, one parameter. So I want to estimate what is the probability of y given x. So I'm using the classical formula for that. So just remember your 101 statistical course. So this is a formula that will allow you to maximize the likelihood of this hyperparameter. So we are just counting how many xi, yj divided by the number of xi. But when you have prior, you can also mix virtual particles that you're going to generate via your Bayesian network. So, because remember that the Bayesian network is a generative model. So you can use particle for learning your model, but you can use your model for generating particles, right? So it's kind of convenient. So here, I'm using a Bayesian network that represents my prior for generating virtual particles that I'm mixing with those that I have in my data set. So one way to do that is to use a smooth probability estimation. So I guess you are familiar with this option in BayesiaLab. So this is something where we are still using, obviously, the particle described in the data set, but we are adding usually one virtual particle. And where our prior is just the fully unconnected network, where all the distributions are uniform. So our prior knowledge is that everything is possible. And it's a very good prior, right? You always have to use this one, indeed. So here you start with everything is possible. So it's a kind of non-informative prior or Laplace correction, if you want. And then based on this network, we are going to generate one virtual particle that is going to be split uniformly across the joint probability distribution. This way, you will never, ever have something with zero in your set, right? So this is convenient because then, if you don't do that, you can always face some configurations that are impossible in your Bayesian network. And then you are not going to be able to use your Bayesian network for processing these particles. So with this option, you can be sure that you will be always able to process all particles, even those that you did not see. The second way to generate prior samples directly prior is to use a generate prior sample feature, which is more difficult because you need to have a fully specified Bayesian network, right? So it's not just fully unconnected and uniform. You need to use your expert knowledge to define Bayesian network in this domain, right? So either you do that by using expert knowledge, or perhaps you already learn a network on a previous data set, right? So, but you have a fully specified Bayesian network, and then same thing, we are going to generate virtual particles by using this prior. The third one is something we introduced last year in BayesiaLab 8. This is a sequential parameter updating. So in this one, you also have a fully specified Bayesian network, and usually this is your current Bayesian network. And you set evidence in a monitor. So the evidence can be, on all the nodes or just partial. It can use hard evidence, negative evidence, soft evidence, numerical evidence, any kind of evidence you can have. So you define this particle by using the monitors, and then we use the Bayesian network here to complete the evidence for the nodes for which you don't have evidence, and this gives you a new particle. And you can use this one with those that are already in your network that we are going to regenerate for updating your theta. You have also another one that is a batch parameter updating. So it's a kind of generalization of the other one. Instead of using only one particle, you are defining a group of particles. So either described in a data set or in an evidence scenario file where you can have, again, hard evidence, soft evidence, numerical evidence, and so on. And this one, you can obviously have missing values, right? So these were the way to add, to change or take into account your prior for the estimation of the parameter theta. Now let's talk about taking into account your prior, but also for the structure, right? And you know that when we do machine learning in BayesiaLab, we are using a score for finding what is the best solution, right? And the score is the minimum description length score. And this is a score that has two components. The first one is the complexity of your theory, and the second one is information. But for complexity, this is like, this is something I highly recommend this book. I don't know if you read this book from Kahneman, but in complexity, in science, complexity is considered as a cost, right? Which must be justified by a sufficiently rich set of new and preferably interesting prediction of facts that the existing theory cannot explain. Which means that even though you come up with something very, very powerful, if it's very complex, just to explain something slightly better, you are not going to be able to sell this theory, right? So this is more or less the idea of the MDL score tool. We are just going to increase the complexity of the network if we can explain more the data. Right? So the second part of the MDL is based on information theory. So the MDL score is a Bayesian score at the end of the day, where you have complexity theory and information theory. So this is the formula for, I think it's always good to have some mathematical formula in a presentation, right? So this is the MDL score for one node here. And if you look at it, this part, this is the way we are estimating the complexity of the network, right? So this is purely for describing the graph. So we are just estimating how many bits we need to represent the structure, the qualitative part. This is for estimating how many bits we need to represent the parameters in this network. So the more parents you have, the bigger these tables will be. And then the more bits you are going to need for representing this network, right? So this is based on information theory. So here, these two parts are more or less heuristic, right? So this is our decision in the MDL score to encode the complexity with this formula. But this one is 100% coming from information theory. So this is just the likelihood of the data given or likelihood of your model given your data, right? So this is log likelihood. So this is for the complexity. This is for information. And once you have that, so we are really, our prior is based on complexity, right? So this is what we use for implementing the Occam razor, right? So if we have various networks with exact same quality with respect to the information, then we are going to choose the simplest one. So the prior is, the priority of a network is proportional or inversely proportional to its complexity. Okay? And you can do in BayesiaLab, you can slightly change the weight of your prior. So the first parameter you can use is what we call the structural coefficient. So I guess you are familiar with this one. So this is just a weight that allows you to, well, a parameter that allows you to change the weight of the complexity part. Right? But you have also the local structural coefficient. So this, I'm not sure you are familiar with this, but you can also define a structural coefficient per node. And now we have added a new one, which is a structural prior. So this will allow you to define a kind of structural coefficient for one arc, right? So it's not at the, it's at the node level, but not only at the node level, but also at the arc level. So in order to define this structural prior, you have a parameter that goes from -1 to 1. So -1 means that you are going to have a strong penalty for adding the link. 1, you are greatly reducing the cost for representing this link, right? So this is something you can do manually. You can select the arc or add the arc manually and then define your structural prior for this link. And I just want to emphasize that if you set -1, it's not gonna forbid the relation, right? So this is just your prior. So if data shows that it's important to have this link, we are still going to add this link. Right? Same thing for 1. If you set 1 and it's not supported by data, we are not going to add the link. So it's not like if you really want to forbid a link, there is a feature in BayesiaLab that allows you to do that. You make a right-click on the link and you say forbid. If you want to add an arc and fix it, same thing, you make a right-click, you fix it, and BayesiaLab will not remove this link. So just a slide here to emphasize the difference between the structural prior and the other way to generate the priors, that was the generate prior samples. When I say it was not easy to use this one, it's because you need to have a fully specified Bayesian network, right? So if you have 200 nodes and you just have the knowledge for a subset of links, you cannot use this one because you really need to define the entire network. But with a structural prior, you can really just define your prior on a subset of links. You don't need to define everything, right? So this is much more flexible. Now let's switch to resampling. Resampling is a set of methods we have, and I'm going to just focus on one particular. This is what we call the data perturbation, and this is also what I call the smooth bootstrapping. You know, with bootstrap, you are generating data set by, you draw in your data and with replacement, right? So with that, you can be confident that you are going to remove 38% of your data. Some will be duplicated, some will be there 3 times, 4 times, 5 times. So bootstrap is not recommended for Bayesian network because it can be good from a statistical point of view for estimating one parameter, but for the structure, there is a huge bias because you are replicating the relationship between all the nodes. So there is a danger here. But with a smooth bootstrap, we are reducing this problem. And I'm going to start with data perturbation that we use for structural learning. So when you use data perturbation for structural learning, the idea is to try to escape from some local optima, right? So we are perturbing the data. And now, so with weights, I don't know if you're familiar with this one, perhaps just a few words. With data perturbation, we are randomly choosing a weight from 0 to 2. But it's a continuous weight. So worst case scenario, you are removing the particles, and the other way around, you are duplicating it. But you can also have 0.9, 1.2, and all these values between the range 0 and 2. So with data perturbation, when we are using that for machine learning, now we have also added a way to perturb the structural coefficient, right? So which means that it's like also a way to change the size of your data set. So this is something you can define here. So for data perturbation and machine learning, we start with a standard deviation equal to 1 for the weight, for the very first try. And so here I'm learning 100 networks. So I'm going to start with a very strong perturbation. But the very last test I'm going to do is with a standard deviation equal to 0, which means that I'm not going to perturb the last data set. Because it's like simulated annealing, so we are really shaking the data at the very beginning and then trying to reduce the perturbation just to see if we can escape from some local minima. And this is brand new. This is a way to explore also the size or the structural coefficient. So you define here also a standard deviation for the structural coefficient. So here I set 1. And you can define a mean and a max. So be careful with the mean, because if you set something equal to 0, you're going to end up with a fully connected network, which is not good. And so the max is just here because I just want to explore. I don't have lots of data. I'm just going to explore the lowest value. If you click on this icon, it's just a way to kind of wizard that will give you what are the mean, structural coefficient, and max that you can have with this standard deviation. So it's a kind of help here. So with that, so as I said, I have my original data set. And I'm going to generate 100 data sets with different weights, different structural coefficients. So this is the reason why you have different colors for the weight and different size for the structural coefficient. Once I have these 100 data sets, I'm going to learn a Bayesian network. Right? And then, at the very end, I'm going to compute the score of this 100 network with the unperturbed data set, with the original one, and see if I was able to escape from a local minimum. So this is data perturbation for structural learning. Now we have also used this approach for learning the structural prior. So this is what we can qualify a bagging method, right? So same thing, we perturb the data, and we use that for learning networks, right? And we are computing statistics on the connection we found, right? So here, I define the learning algorithm I want to use, sublake, then my structural coefficient and the range, so from 0.1 to 4, I'm really trying to reduce the structural coefficient and also to increase it. And then here I'm going to remove the current set of prior, because if you don't do that, you are going to use the previous one. And I have then the workflow, same thing, 100 data set. I'm using my sublake algorithm here for learning 100 Bayesian networks. And I'm using now these networks to compute statistics to build my structural prior. And these prior are going to be used for learning the final Bayesian network. Right? So we can this way, estimate the prior of our link just by using this bagging approach. So you just have to be careful to remove this prior if you don't want to use it, because once they are defined, they are going to stay there. Right? So this is a very powerful approach now that allows you to deal with data sets that are small. Before you had to play with the structural coefficient, now it's automatic, you don't have to do anything. This will explore the structural coefficient for you and gives you something that is kind of stable, robust. So we have also used this approach for defining a partial ordering. So still, it's a bagging approach. So we do perturbation, then we learn Bayesian networks, but then we are transforming this Bayesian network into essential graphs. So if you are not familiar with essential graphs, these are a graph where you have at the same time edges and arcs. So we are removing the orientation of the links that can be set in both directions without changing the joint probability distribution. And then, so we are representing the partial ordering by using temporal indexes. So this is here an example with a famous network called car start here. So if I do here partial ordering, so I just want here to compare the partial ordering with a feature we added last year, which allows you to compute the depth of the nodes. So by using a class here. So if you estimate the depth of the nodes here, you're going to have these blue nodes. The root nodes will belong to the depth 0. Those with at least one parent will belong to the depth 1, and so on and so forth. Right? So at the end of the day, you have stars here that belong to this 4th layer or 5th layer. That is, right? But with essential graph, it's different because, as I said, we are using essential graphs. So for, in that case, battery states that belong to depth 1 with the other feature here still belong to the order 0 because it's undirected here. So I can only have a directed link if I have a V structure, at least. So if this is just AB, we know that AB, BA, we cannot define any direction, right? Unless this is set by expert knowledge. So this is partial ordering. And this is something you can also generate. So when you have a network, you can go through analysis report graph partial ordering. And this will compute or estimate the temporal indexes given this graph. So as I said, we are using bagging for estimating the partial ordering. So the workflow is the same as before. You can also remove the current temporal indexes. And we are creating 100 data sets. Then we are machine learning 100 networks. Then we are analyzing the essential graphs, and we extract the partial orders, right? And we have temporal indexes. So there is also an option. So either you have integers, or you can also, so integers, we are, at the end of the day, estimating the temporal indexing by voting. So we are taking the max. But you can also choose to have a double or a continuous value. In that case, it's the average of the order, right? And same thing, these temporal indexes will remain valid unless you remove them manually. So you see that this can be a step that can be useful if you are looking for causal discovery, because now we are really using essential graphs, which are not Bayesian networks. So we are closer to causalities than with just a Bayesian network. We also have a new layout algorithm that uses these temporal indexes. So Here, this is a layout that just organizes your node by using the temporal indexes. And the last topic with this resampling approach is to do cross-validation for your variable clustering. So I'm not sure everybody uses variable clustering. So the idea is to analyze the network you have that represents the joint priority distribution, and then use the strength of the connection between the nodes to define groups of nodes. Right? So it's a kind of competing approach for factorial analysis, but where you are creating factors that are not orthogonal, and just it's really like changing the zoom in an image, right? Where your nodes are pixels. So here you can also do cross-validation for this approach. And so you define your algorithm. You define then the settings for variable clustering, and then the settings for the cross-validation. So again, here I'm using 100 test set. I'm not exploring here the structural coefficient. So I said 0, so just to keep the same one. And here, so we learn, again, 100 Bayesian network, but this means that here this is learning a Bayesian network, then using variable clustering with the setting I've just defined, and then we do statistics on the factors we found. Right? And with that, you have now a new table that gives you the node association frequencies. So you can see lots of colors as usual in BayesiaLab. So the nodes that are in green belong to the same factor in my current Bayesian network. So what matters here is are the cells that are also in green, because these are what we can call the co-manifest, the variables that belong to the same factor in the original network. So you really care about the frequency that is in the same color. And this is what we use for defining the purity now of a node. Right? So the purity of a node will be the average value of this association frequency with the co-manifest variable. And then we can also define a purity of the solution of each factor by taking into account the purity of all the nodes that belong to this factor. And then you have these tools that were there before, that allows you to have a kind of summary of all the factors that have been learned. So here it's obviously not a Bayesian network. It's a graph where you see that when you have a connection between two nodes, this means that these two nodes have at least been grouped together in one factor. So the width of the link is directly proportional to the frequency of association. And so usually it's a kind of mess here. So we added a filter that allows you to define what is the minimum frequency you want to have. So this way you can really measure the stability of your clustering. Right? Then we also added a new feature for generating code that useful for computing the priority of a target node. So for based on the Markov blanket. So just a reminder of what is a Markov blanket. So you have your node, your target node here, and the Markov blanket is defined as a parent, children, and spouses. Right? And these are the nodes that if you have hard evidence on these nodes, then your target is conditionally independent of all the other nodes. So it's a very convenient property because even though you have 20,000 nodes, if you have been able to identify the Markov blanket, you don't need the other one. Right? So we have lots of ways to generate code for computing this Markov blanket or the priority of the target node based on the Markov blanket. So we have a way to generate PHP, JavaScript, Visual Basic, SAS, and R, and now Python because of you, Stephen. We are always close to our customer, right? So now you can generate a code in Python. And so this is the example with this target node here, BMI. You generate the code, and then you have this Python code that is generated that you can use. You don't need BayesiaLab then for computing the priority of your target node. Right? And I'm going to conclude with the last one, media. So media, this is something that is directly linked to the training I'm giving. As you can see, I'm traveling a lot, giving training everywhere. And so now we have an option where you don't have to be there. You can follow the training live stream, right? So this is So the slide I'm using for describing the very nice journey of this, the discovery of the field of Bayesian network, very, very dense one. So we have 2 training sessions, right? So we have what we call the intro course, 3 days, and then the advanced course, also 3 days. Some of you here went already Monday, Tuesday, and yesterday to the intro course. Then you have the conference, and then you have the advanced course next week too. So for those who have stamina, you can join the advanced course. We still have some free seats, available seats, not free. And so when I'm doing this training session now, so this is, for those who are live stream, we are using GoToMeeting so for sharing the screen and the voice. And we are also recording the training. So this way, those who were in the training, they can, during 3 months, they have access to the video, so they can go through the training again and again, because I know that we are covering so many topics that it's just impossible to get everything. So with that, you can take your time and digest everything. So now we have the training in English, we have the training in French for this intro and advanced course. And you can also, use that asynchronous, so you don't have to be there. You don't have to subscribe for a live stream option. You can also say, oh, I'm going to purchase this intro course and follow that when I have some time. Right? And the PDF, so the slides I'm using during the training are available, but it's via BayesiaLab, so you have to go to the help menu, then go to media, and then you have the list of all the slides here. So everything has been split into chapters, and you have the same thing for the videos, right? So then you can really watch the videos, and this is where I really realized that during these 3 days of the intro course, I'm just talking during 20 hours nonstop, right? So now the intro course, there is almost no breaks, right? So these are the main feature I wanted to talk about. Obviously, we have other features, but yes, I think it's already time. So this is something we are going to release in a few weeks, and I hope you are going to enjoy these new features. And you are always welcome to suggest new features, right? So either via the forum we have on our website, or directly send emails or phone calls. Thank you for your attention.